Hello and welcome to the second part of video lecture of chapter 12. In this lecture I will be covering the remaining topics of chapter 12, including section 12.7, which is rotation about a fixed axis. We're going to do a bunch of problems, and then I'll be covering static equilibrium. That is section 12.8. There are 4 examples there in the book that are really good. I'm not going to do all of them, but I'm going to do, I would say, 2 of them. Example 12, 13, 14, 15, 3 examples actually. And then we will move to the last topic, and that is angular momentum. Okay, this is section 12.11. And then there are some remaining stuff that we're not going to cover. The last one is called precession of the gyroscope, which is not something that I'm going to cover. That's kind of an advanced mechanic, so I'm not going to cover that. Anyway, I will begin with the example that you see around you right here, 12.11. Before I do that, let's just recap what we covered in the first part. And we covered the subject of torque. And we said that tau as a vector is equal to r cross f. R is the moment arm, and F is the applied force, right? And the scalar version of it is tau is equal to r f sine the angle between the moment arm and the force, right? And then this is analogous to Newton's second law, which is F equals ma, where, as we said, ma is the kinetic reaction, and this is the sum of the forces, if you will, the net force, right? And the net force produces a kinetic reaction. Similarly, we have the net torque on an object produces a kinetic reaction. Maybe we would call it rotational kinetic reaction, and it is equal to I alpha. Alpha being the angular acceleration, and the I here is the moment of inertia, MOI, I'll call it, okay? And that would be the net torque, okay? So I'm going to be doing some examples. I think we've done maybe a couple. I don't remember how many we did, but I'll do some more examples on that. So we will begin with example from the book 12.11. Here it is. Let's read it together. It says starting an airplane engine. Okay, it says the engine in a small airplane is specified to have a torque of 60 Newton meter. Okay, remember the unit of torque is Newton meter. I would say more appropriately meter Newton, because it is, you know, the torque, if you remember, it's right here. It is R cross F, and the cross product is not commutative. It means R cross F is not equal to F cross R. So it is important that you have to, the order is important. So if it is tau is equal to RF, so the unit in this case will be meter Newton. So if you really don't want to be specific, it's actually meter Newton rather than Newton meter. But that's just, you know, just details. But anyway, okay. So let's write down what's given to us here. He says you have what do you call it? You have an airplane engine, and then you get that fan, whatever you call that thing. And we have a torque of 60 Newton meter. This engine drives a 2 meter long 40 kilogram propeller. I guess that's the proper name for it, propeller. Okay, so we have the length of this. We're going to see it as a rod, remember that. So this approximates a rod rotating about its center. Remember, you go back to the table and you see the moment of inertia of a rod rotating about the center. If I remember correctly, it's 1/12 ml squared, L being the length of it, okay? All right, and then the mass of it is 40 kilogram. On startup, which means initially, how long does it take for the propeller, or how does it take the propeller to reach 200 RPM? Okay, so we have here the frequency, 200 revolution per minute. Okay, how long it will take it. So here we're talking here about not just torque, but we're talking about rotational kinematics. You know what I mean? Remember the rotational kinematics? Let me write them down very quickly. Rotational kinematics, if you remember kinematics, the equation of kinematics, you should be able to remember them. Omega equals omega naught plus 2, what is it? Alpha t. And then we have omega squared, equal omega naught squared plus 2 alpha theta, correct? And then we have theta equals omega naught t plus 1/2 alpha t squared. These are the rotational kinematics, and those are the ones that we're going to be using, okay? So let's write down what's given. So we said that the torque, the scalar value of it, is 60. I'm looking at my book here in front of me, 60 Newton meter. And the length of the rod, let's just call it rod, or propeller, is 2 meters. And then we have the mass of that rod is 40 kilogram. And we have also the frequency, he said, is 200 RPM, which is rev per min, right? We want to convert it to rev per sec. And then what else do we have? And that's it. So he's saying how long it will take the propeller to, oh, sorry, this is the how long it will reach that, okay? So he's asking for time, how long it will take it, okay? All right. So if I am going to be using, most likely I'm going to be using those equations of kinematics. I don't know yet which one to use, if you know what I mean. However, I know for a fact that I have to get alpha, right? I have to get the value of alpha here. So this alpha. See, every one of them has angular acceleration. So I need to get that alpha. Once I get that, then probably I'm good to go, okay? So the first thing I need to do is to use dynamics, and that is the torque. Well, let me make a diagram of this thing. So we're going to make it, what we're going to do, we're going to draw it as if it is a rod, okay? So here it is. I mean, at least we'll treat it as a rod. I'll just make it into, how do I do this? I'll try to draw it as good as I can. Here's one part of it. Here's the other part. Make it as equal as possible. There we go. Okay. And so here's the axis of rotation is right there. Right. And then it is rotating like that. Okay. And this is the axis of rotation. And then you have the length of the rod is 2 meters. And the mass of it is 40 kilogram. Okay, so I will start by writing the torque equation. Why? Because the torque equation contains alpha. You know, sigma tau equals I alpha. I really don't need a sigma because it's just one torque here. It's not a complicated system. We'll deal with other complicated system later. But so from there I can find alpha in this case, okay? I here is for a rod about the center. You can look up the table, is 1/12 ml squared. And so therefore, in this case, tau, I am copying from here. So tau in this case will be equal to 1/12 ml squared times alpha. And therefore, alpha is equal to 12 tau over ml squared. Is that right? Plug in the numbers. So I have 12. Torque is 60. Mass is 40. And L squared is 2 squared, right? And then I would calculate that. And when I do the calculations, I will end up with 4.5 radian per second squared. Remember the unit of alpha, okay? So there we go. I got the alpha value. Okay? All right. Now, so now he's asking me for the time. So I can just immediately go to one of the kinematic equations here. Now, the latter two, this one and this one, contain theta. See that? Let me use a different color. Okay, say they have theta here, which I don't have much information about. The first equation doesn't have the theta, so I'm gonna go with this one. He says at startup, which means omega naught is 0, correct? So basically what I have is omega equal to alpha t. Okay, so I need to get, and then from there I can find the time. You see the plan? Okay, so I go back and write it down. So I have here omega equals omega naught plus alpha t. Omega naught is 0. Why? Because it said, let me take you there again. It says on startup, which means what? It wasn't moving. It wasn't spinning, if you will. So omega naught is 0. And I need to find omega. Well, he gives me the frequency. F equals 200 rev per minute, for that matter. So that means 200 over 60 hertz. Is that right? And that will give me, let me use my calculator. I'll have 200 divided by 60. I hope you're working with me. And I get 3.33. So I have the frequency is 3.33 hertz. Okay? There we go. Now, omega, well, omega is 2 pi f, right? So in this case, I can just quickly put it here. So that will be 2 pi f equals alpha t. So therefore, t is equal to 2 pi f over alpha. That's it. I'm done with the problem, really. So you have 2 pi times the frequency, which is 3.33, divided by alpha, 4.5. And then when I calculate that, I will end up with 4.65 seconds. And there we go. I got the time. You got it? Okay. Next problem. This one. Example 1212. This one can be hard to some of you, so pay attention to it. Let me show it to you in the book. It should be down here somewhere. There it is, right here. Okay, so you have something like a pulley, and it's spinning, and then you got that bucket. You know, it's like something on top of a well. And so anyway, let's read it. It says a 2 kilogram. Sorry, I arranged some stuff out of my desk. Okay, it says a 2 kilogram bucket is attached to a massless string, so we're not taking the mass of the string into consideration, that is wrapped around a 1 kilogram 4 centimeter diameter cylinder. We can call it a drum or something, as shown in the figure right there. The cylinder rotates on an axle through the center. The bucket is released from rest, so that means omega naught is 0, maybe, something like that, or V naught, something like this, from rest 1 meter above the floor. So here is the floor right here, and the bucket was there at t equals 0, and then it released at 1 meter above it. He said how long it will take it to reach the floor. Okay? All right. So how do we do it? Well, let's see. Let me make a drawing of this thing. I can think of 2 diagrams to do it. Let me change the color to black. So here is the first drawing. I'm going to do 2 drawings here. The first one is the one shown in the book, and it looks something like that. Here is the cylinder. It's not a good cylinder. Sorry. Just go like this. Then you get the, here is the string wrapped around it like that, right? And then I have, here is the axis of rotation. I like to draw it because it kind of help me visualize it. See, you have to be able to visualize the problem in order to solve it. If you cannot visualize it, then it becomes really hard to do. So you have to run a film in your head, as I told you in the past. So here is the mass here. I'm going to call it small m. Okay? And it's going down. And of course, you have, here is the height of 1 meter, he says. And he also says, this is example 12.12. He said omega naught is 0, V naught is 0. I'm not sure which one it's useful for us. Anyway, so it is spinning, let's assume, again, just to help me visualize it, it's spinning like that. This is alpha, okay? That's the axis of rotation here, okay? And what's given to us? He said the mass of the bucket is 2 kilograms. I'm sorry, let me go back. There is a 2 kilogram bucket, okay, and then you have a 1 kilogram cylinder. So the mass of the cylinder, let me call the mass of the cylinder big M, is that okay? So the cylinder big M is 1 kilogram. This is the mass of the bucket. This is the mass of the drum or the cylinder, okay? And he also, what else he gives us information? He says it's a 4 centimeter diameter. So the radius here, in this case, is going to be 2 centimeters. So that will be 0.02 meters, right? The cylinder rotates about an axle. We get that. Okay, so he said how long it will take it to reach the floor. All right, so he's looking for the time. Okay, so how do we do this problem? Well, what you want to do, again, it most likely there is some kinematics involved here. And since he's asking for the time for the bucket here to go all the way here, so I'm probably looking at translational kinematics. You know, the V equals V naught plus AT, V squared equals V naught squared plus 2AX, 2AY there for our case, and then Y equals V naught T plus 1/2 AT squared. These are the those are probably the equations that I'm going to be looking at to find that time from here to there. You see what I'm saying? Again, I'm just, what I'm doing right now, I'm just speaking my thought for you, okay? So maybe it looks like most likely I use the third equation, but I could be wrong. This one right here. Okay, but before I do that, I need to find the acceleration. You see what I'm saying? I have to find the acceleration here. Given the fact that the bucket or the what do you call it? Not the bucket. The cylinder is spinning, right? It's spinning like that. So I'm going to use the torque equation. So let me make a drawing of that, a better drawing, a 2D drawing, two-dimensional. So here is the drum of the cylinder. Okay, and here is the radius. If I can draw a better R, there we go. And it, of course, is spinning like that. Here is the string, and that's the mass right here, the small m. This one is the big M, okay? And of course, the whole system is going down like that. Okay, now, what are the forces on it? Well, you get the mg here, and you get the tension. Remember, tension always comes out of the body. There we go. And then it is going down with some acceleration a, correct? So with this, I can immediately get the equation of motion, you know, using F equals ma. So here we have sum of the forces equals ma, m here being the mass of the bucket, right? So in this case, I'll have T minus mg equals ma. You see what I'm saying? And there we go. I'm basically done with this. So T equal to ma plus mg. I can say that it is ma plus g as a common, m is a common factor. So I have this equation. That's not very helpful a lot. Why? Because I don't know the tension, T, and I don't know the acceleration as well. So I don't know those. You know what I'm saying? I don't know how to do them. I don't know how to get them. So what I do now, I appeal to the torque equation because this whole system is spinning, right? This whole system is, let me use my mouse so you can see what I'm doing. This whole system is spinning here. So I can use the torque equation to help me hopefully find A or T, one of them. Most likely I'll be able to find T. Let me show you how. All right, so pay attention to this diagram that I've drawn right here. And let's take the torque about a point. Always take the torque about a point, okay? So probably the most convenient point would be the origin right here, okay? The dot right there, so I'm going to call that O right there, maybe I'll just take this, just call it O. So what we want to do, sum of the torque about O, okay, and that's going to give me I alpha. It's not zero, it's spinning, it's rotating, and therefore there is a rotational kinetic reaction, I alpha. I don't know the alpha, okay? I know the I, okay, he said it's a cylinder, so I know I for a cylinder. I memorize it, you can look it up, 1/2 mr squared. The m here, the big M here, being the mass of the drum, the drum or the cylinder, whatever, okay? And then I'm gonna get the torque. The torque, remember, tau is what? Rf. And pay very good attention whether it's clockwise or counterclockwise. If it's clockwise, it's negative. If it's counterclockwise, it's positive. This is our sign convention, okay? All right, so let's do it. So here is the R here is really for us is the big R. So in a way, I can see it this way, big RF, okay? Where F symbolizes the forces. Well, how many forces do we have? I'll tell you how. I'm going to draw this same diagram here, this one more time, but tailored specifically for torque. So here is the drum. Here is the radius. And here is the force. That's it. This is the force that is causing the rotation. You got that? Well, what is that force? Well, it's nothing but the tension. Is that right? I mean, the tension, remember I told you it's always out of the body. Well, here is the tension, and here is the same tension right there. Action reaction. It's always out of the body. So, and this T, and guess what? I already know what T is right here. You see that? That's the tension right here. So, all right. Now, oops. Now, what I'm going to do, take the torque about O. So we're going to be RF. See that? Imagine T would go with the mouse so you can see what I'm doing. So RF. Well, excuse me, RF with F is T here. So RF or RT, and this T is going to rotate like that. See the direction of motion? Well, is that clockwise or counterclockwise? That's counterclockwise, right? Positive. So in this case, sigma tau right here is going to be RT equals I alpha. Positive. Because it's counterclockwise. Well, what is T? T is right there. So therefore, R M A plus G equals I alpha. I already know what I is, but hang on a minute. So I'll just put it like that, okay? And then I am basically solving for alpha. Why? I'll tell you in a minute why. So my goal is to solve for alpha, okay? So I'm going to work it out solving for alpha. Okay, let's see. So it's going to be RMA plus RMG equals to 1/2 big M R squared alpha, okay? So this R, oops, R cancel out, just go like this, better. All right, and so what I'm going to have here, let me take, let's see, let me write it down again. I'm going to show you something here interesting. MA plus MG equals 1/2 big M alpha, okay? Now, remember, I'm not interested in the alpha. I'm really interested in the A, not alpha, because remember I told you about that kinematic equation. So I'm not really interested in alpha. So here is how it works. There is a little trick that you want to keep in mind. If you want to get rid of alpha, well, I know that A is equal to alpha R. You see that? That's how you eliminate the alpha. So alpha is just A over big R. There it is. And that's how I eliminate this alpha. So now I can plug it in there. So it becomes MA plus MG. Remember, those M's are for the bucket. Plus equals 1/2 big M A over R. And now all I need to do is to solve for A. Basically, you know, just do the algebra and get the value of A. When you work it out, you're going to get this one. Here it is. I already did it. I'm looking at it in my notes. So it's going to be minus mg, this is a small m, over small m plus big M over 2. Okay? There we go. I have an expression for A. Next step, well, I got all the numbers, just plug it in. So A, in this case, it will be equal to, I have the minus here, and then it's going to be, what is it, 9.8 divided by 2, plus the mass is 1 over 2. Calculate all of that, you'll get the acceleration equals to negative 7.84, okay? Now, my answer, for me, it makes sense to me because it's a negative, you know, it is downward acceleration. So that should be, so that just tells me, you know, that I'm doing it correctly, probably, most likely, okay? All right, that's it. So now I go back to the kinematics. The third kinematic equation, probably the most convenient, y equals v naught t plus 1/2 at squared. And then this is 0. So he's asking for the time, so that will be 2y over a under the square root. Plug it in, and you will get 1 over 7.84. Should I put the minus sign there? Sure, you want to, go ahead. But here is how it works. I want to be, I didn't make any mistake, but I'm going to show you what I'm doing here. All right, if I'm going to be very specific, I have to put the minus sign for the acceleration. Well, I have to also take care of the y. The y is also negative, right? It's below the bucket. So that's going to be negative 1 over negative 7.84 to the 1/2. And then you get the time. It's equal to 1/2 second, 0.5 second. And there we go. And there we go. It will take the bucket 1/2 second to reach the floor. Got it? Okay. Now let's do something a little bit heavier. Example 1214. All right. I urge you to look at example 1210. Let me write it down. I'm not going to do them because there's just too many of them, too many good ones. Practice examples 1210 and 1213. I'm going to do 14 and 15, okay? So let's do them. Okay, example 14. This one a little toughy. And I believe there is a problem in the homework similar to it. So pay attention to it. Example 1214. Okay, he said, oh, let's go to it. I need to know how far is it. Oh, the next page from this example. Oh, okay. Yeah, well, you may want to read 1213, but anyway, okay. There we go. This one. This one is very interesting, and it can be hard. Look at that. There is a plank, okay? There is a beam or a piece of wood right there, and there are two supports here, okay? And then you got those two individuals. One individual is standing right at the edge of the plank, and the other person is moving away from it, okay? Now, at a certain distance, as you can see, it's going to tip over. Make sense? It's going to tip over a certain distance, okay? And he's asking at what distance it's going to tip over. See how tough this problem is? Interesting. Let's read it. So you have Adrian, 50 kilograms, which is right here, and Bo, kind of a funny name, 90 kilogram. So, okay, so we have the guy is 90 kilogram, this one, she is 50 kilogram, are playing on a 100 kilogram rigid plank, resting on the supports. If Adrian stands on the left end, okay, so she's not moving at all, okay, can Bo walk all the way to the right end without the plank tipping over? If not, this is really what I'm interested in. how far can he get past the support to the right? In other words, he's asking for that value of x from somewhere, okay? So let's look at this problem, and I'm going to solve it my method. I'm not sure how he did it. I'm going to do it my way. All right, let me move this to the side without getting out of the screen. It probably should be good enough here. There we go. Okay, so let's draw it. So I have here is the plank right here. Just give me a second to draw it. And here is, we'll call it Adrian. Sorry, I can make it prettier. But anyway. Okay, so then we have the support. One support is right there, and another support is right here. And then you get Bo right there. He's walking, but I can't draw somebody walking. I don't know how to do that. Anyway, there we go. And let me make it a little bit. Oh, I don't want to do that. I can't do undo. I don't know if that's possible. But anyway, I'm just do it again. I want to make it a little bit longer. There we go. Okay, there we go. Okay, and he says the entire, okay, so the mass of Bo, we're going to call him M sub B, is 90 kilogram. Adrian, I'm going to call it M sub D, okay? D for Adrian is 50 kilogram. And then you have the support. Look at that picture right here, guys, okay? So the support is from here. Those dimensions are important, okay? So and then the distance between the two supports is 3. And then we have the rest of it is 4. Okay, there we go. Now another thing, he says that the mass of the plank is 100 kilogram. There we go. Okay, and so that means I have to take care of the center of mass. So the center of mass, well, what's the total length of the plank? 2 plus 3 plus 4, that will make it 9. So that will be a 4.5. So it's roughly, sorry, the image is not drawn to scale. So it's going to be somewhere here. That will be the center of mass of the thing, right? So in other words, how far is it? Well, let me put a different color. And I need to put the dimensions correctly in order for me to solve it right. So this is 4.5 here. I'll tell you in a minute why I'm doing all that. This is 4.5. And if this is, so what is the, okay, we'll just stop here. Okay. Now, another drawing that I want to do is this. Go back. Now I'm going to put the forces. Okay, I'm going to turn it into a Freebody diagram. So here it is. Watch how I do it. So here is the plank, or the beam, engineers would call it. Here is one support. Here is the center of mass. Here is the other support. Here is the Adrian. Okay, I'll make it into a box, and I make this guy. I'll put him at some arbitrary distance. We don't know where he is, right? So we're going to call that Bo, and that's Adrian, D, if you will. And so what do we have? What are the forces here? Well, I'm going to get MBG, M sub DG, and then I'm going to get a normal here. I'm going to call it N1. And this is another normal. I'm going to call it N2. You agree with me on that? And then we have the mass or the weight of the plank, MPG. Got it? There we go. These are the forces that I have. Now here is a question. What's the condition in terms of those forces that you're looking at? I got how many forces? 1, 2, 3, 4, 5. What's the condition that will allow the plank to tip over? Okay? Well, the condition is when N1 becomes 0. Make sense? See, it's going to tip over, and the support is going to be, it's going to tip over this point right here. You see what I'm saying? So N1 becomes 0. So the condition for tipping over is when N equals 0. So condition to tip over when N1 equals 0. See what I'm saying? Okay, so before I go any further, let me write down some of the forces equal. I'll put them here. So sum of the forces equals 0. There's no MA, right? There's nothing here. There's no MA. It's all static situation. So I'm going to have here N1 plus N2 minus MdG, the weight of Adrian, minus the weight of the plank, which is mpg, minus the weight of bow, mbg, equals 0. All right? So condition is that when, let me just say it this way, when n1 goes to 0, what's going to happen? Well, let's write down the equation. How is it going to look like? Well, let me solve for n2 here, okay? I'll tell you in a minute why I'm doing n2, because, well, I'll tell you now. n2, I don't know the value of n2. I know nothing about it. I know the value of everything else. All the other forces, I know them all. I don't know n2. So I can actually solve and get the answer for n2. So what is n2? Well, n2 in this case is going to be equal to md plus mp plus mb quantity g. Is that right? I can get a number out of that. So Adrian is 50, plank is 100, bow is 90, g, and that will be equal to 150, 240. Is that right? 240? 50? Yeah, 240 G. Let me call it 240 G. Just to give it a nice looking number. G is 9.8, of course, right? It's not gram or anything. All right. Oops, N2 here. There we go. I'm going to box it and come back to it. All right. Now, remember, I am not, see, Newtonian formula, sigma F equals ma or equals 0, it doesn't give you the distance. Yeah, I mean, it gives me what is the value of N2 when the plank tip over. You see what I'm saying? It will tell me that. But it doesn't tell me at what distance, where exactly, it doesn't give me. So that's why I need to appeal to the torque formula. You got that? So how do I do that? Well, I just want to take the torque. So I'm going to go sum of the torque equals 0. About what? About what point? Well, the easiest point in the world is to take it about N1. You can put it on something else, but I don't know what N1 is. So I'm going to put it right here. So I'm going to call this point A, or whatever you want to call it. So sigma tau about A is equal to 0. And keep in mind, clockwise is negative, counterclockwise is positive. Before I do that, let's put in some distances here, so we get everything, oops. I'll pick green, okay? So remember, I'm going to take the torque about A right here. So what's the distance from here to here? This is going to be 2, right? And then from here to here is what? I remember this, from here to here is 3. So this is 2.5. Is that right, guys? 2.5? Yes. And this is 0.5 here. And then, what else? And then from here to where bow is, remember, I'm taking the torque about O. So from A to where bow is, I don't know. I'm going to call it X. And that's really what I'm looking for. Got it? Okay. So let's take the torque about A. Let's start with the Adrian right here. So that's going to be, look at that vector, and put it on a mouse. Look at that vector. So you get this vector. This vector is going to go about A like that. See that? It's going to go about it like that. Well, that's clockwise or counterclockwise? You can use the right hand. It's summed up. That's going to be positive, right? So that's going to be plus. That's going to be 2 mdg, right? Now take the torque about A due to the weight of the plank, which is going to go this way. That's that's clockwise. It's going to be negative, right? So that's going to be minus mpg. I'll come back and put the numbers in a minute. Times, how far is it? 2.5. And then N2, well, N2 is going to go around this way. That's a counterclockwise. So that's going to be plus N2. And how far is it from A? It's 3. Is that right? And then the last one, Bo. Well, Bo, how far is it? How far is he? Well, X. So that's going to be, and then it is going down this way, this way. What is that? That's clockwise, right? So that's going to be minus M Bo G times X equals 0. As you can see, I'm done with the problem. All I need to do, take this N2 right here, plug it right there, right? And then I have everything else. Let me just go one more step. So it's going to be 2 times 50 times 9.8 minus Planck is 100, 2.5 times 9.8 plus 3 times N2 is 240 times 9.8 minus Bo is 90 times 9.8. Oh, they all have G, no, except, actually they do, equal, times X equals 0. The 9.8 could cancel out, all of them have 9.8. See how convenient it is when you leave that G there? Anyway, and then you just work it out, it's pretty simple, and you get X to be equal to 6.3 meters. And there we go. Got it? Okay. One more problem, the ladder problem. And that's example number, what is the ladder problem? Oh, it is example 1215. Let me take you there. There we go. This is the ladder. Make sure that you understand the ladder problem. For those of you who plan to take statics and dynamics, if you're in mechanical engineering or civil, you will do a lot of ladder problems. It's just going to be your middle name. So make sure that you understand the ladder problem. So anyway, we're going to do this problem right here. I'll be right back. Okay, it says, here's the problem here. Look at the picture as we read it. He said a 3-meter long ladder. So this is a ladder. 3 meters long, leans against a frictionless wall. So the wall is frictionless at an angle of 60 degrees to the horizontal right there. Do you see it? What is the minimum value of the coefficient of friction that prevents the ladder from slipping? Okay. What's the minimum value of mu sub s prevented from slipping? Okay. First of all, before we do any of that, I'm going to tell you a little bit about the ladder. How does it work? Okay. Well, 15. All right. So it looks something like that. Let me draw the ladder for you. I need to go really slow, otherwise I'll mess it up. I'm really trying. There we go. So here's the ladder. Okay. And what are the forces on it? Well, of course, here we're talking about a ladder with nobody on the ladder. Okay, so it's just a ladder leaning against the wall. So here is the center of mass of the ladder, which is right at the center. So this would be the weight of the ladder, mg, right? And then, of course, you'd have a normal right here, vertical. And then I have another normal. Remember, it's touching a surface. So oops, there is another normal. And that would be like that, and 2. Okay? And anything else? Yes. Well, if it's leaning against the wall, okay, and it is not slipping this way, that means there is a friction force on it going this way, correct? So basically, he's asking for this friction force. If I find this friction force, I can answer his question. But my goal in this problem is really to find the friction force. You got it? Okay. Let me make this just a little bit longer. Here is the friction. I'm just going to make it longer, just trying to make it look prettier. Hold on. This is the friction force, F. That's the angle 60. Okay? All right. Let me change the color. All right. What you want to do is you want to take the torque. I mean, hold on. Let's not take the torque yet. Okay. Let's talk about the sigma F equals ma. We have two forces. Some of the forces in the horizontal direction, like this one and this one, and some in the vertical direction, like this one and this one, right? So sigma Fx equals 0, and then you have sigma Fy equals 0 as well. In the x direction, what do I get? I get minus F plus N2, oops, small n2, right? Equals 0. Okay? The other one, in the y direction, that's just going to be N1 minus mg equals 0. So now the good news is I know a value, or I can actually find out what N1 and N2 are equal to. N2 here is equal to the friction force, and N1 here is basically equal to the weight of the ladder. Okay, great, fine. But I don't know what the friction force. I have too many unknowns, if you know what I mean. Okay. Now this is where we appeal to the torque equation. Okay. Now I want to take the torque. Remember, when I take the torque, sigma tau. Sigma tau. This sigma tau is going to be always about a point. Remember, I put 0 because it's not rotating. So about a point. Which point am I going to choose? You see what I'm saying? Which point? Always choose it about a point where there is a vector or a force on it that you don't know its value. Let me repeat. When you take the torque about a point, always, I mean, you have choices. You can choose it about this point right here. I can choose it about this point right here, about this point right here. I can actually choose it about this point right here. Any random point that I want. Really, I'm free to pick any point I want. But what is the best point to pick? Pick it about a point, okay, where there are some forces on it, such as this one right here, that I don't know their value, such as the F here. I don't know F. So I'm going to take it here. You see what I'm saying? All right. So I'm going to call this point A. Sorry. So I'm going to call this point A. Watch what will happen. Remember, when I take the torque, we said that, let me just review. Tau is equal to Rf, and it is a must that R and F are perpendicular to each other. If they are not, then it is Rf sine the angle, okay? Or cosine. It doesn't, I mean, it depends on which component, such that R and F must be perpendicular. That's the important thing. Okay. So let's look at this diagram here. Let me put another color. Pay attention now. Whoops, what am I doing? I want to go to draw. I want to pick a green color, probably easier. Okay. All right, look at this. If I draw a vertical line here, this angle would be 60, correct? Remember, this angle is 60 right here. And if I draw, I need to get those. There is a reason I'm doing that. If you don't understand, I'll explain it in a minute. Now, if I draw the same vertical line to the, vertical to the, or normal to the ladder, this would be 30, right? Okay. This would be 60, however, right there. You can pick whichever angle you want. What else do I have? And of course, this one here, it would be what? 30, right? Now, when I take the torque about A, I need to take the torque in such a way that here is the moment arm, okay? So this is the length of the ladder is the moment arm, R, okay? And so the force have to be, for mg is going to be, this is the force, going to be perpendicular to R. And the force here is going to be this one, this component, okay? So what I'm trying to say is this. I hope nobody's confused with that. So when I take the torque about A, it's going to be mg, let's start with this one, the mg here. Mg times how far is it? Well, how far is it? It is, remember, we said the length of the ladder. I forgot. What's the length of the ladder? Oh, 3. It's right here. It's 3. So that would be 1.5, correct? How about if I just, for simply, let's call it the length is L. We'll put the numbers later. So that's going to be L over 2. But it's not mg. Remember, this mg is not perpendicular to the length. So I'm going to take this component. So it's going to be cosine 60. Got it? Now, if you want to insist on using sine, that's fine. Here, I'll show you. You don't need cosine. Then you're going to use this angle right here. Let me use a different color again. I'll pick blue. This one. Remember I said that the angle should be between the force and the moment arm. So this is the angle, which is 30. So you can say sine 30. That's fine. Sine 30. Fine. Same thing as cosine 60. It doesn't really matter. Now the next one, well, is it a clockwise or counterclockwise? Well, it's going to go like that. So that will be counterclockwise. That's going to be positive, right? There we go. You see how I constructed it? Now we come to the next one, N2. So I am taking this component of N2. And the angle between them is the 60 degrees, correct? Because this is the length right here. And that's the angle, so that's going to be this. So that's going to be, and it's also, well, if I'm going to take it this way, and that's going to be what? Clockwise. So that's going to be minus N2 sine 60 times L, right? It's L away from A, right? It's L away from A, and that's equal to 0. Personally, the way I would do it, I'm just going to say mg cosine 60 times L over 2 minus N2 cosine 30 L. Again, either method, you'll get you the same thing. Okay? And then we work it out. So with this, I'm going to get N2, solving for N2, and that's going to be mg, what is it, N2? I'm going to use, I'm not going to use this one. I just don't want to confuse anybody. I'll use this one right here. So it's going to be mg over 2. If you work it out, you'll end up with 0.5 over 0.866. And then when you solve it, you'll end up with mg over 2 over square root of 3. I'm going to write it this way if you don't mind. I'm copying this from my notes, by the way. There we go. Okay? Now we come to the friction. I'm done. So now I have already found what N2 is. N2 is equal to that number that I've just gotten right here. And then I already know from this one that N2 is also equal to the friction. Isn't that interesting? I already know what N1 is, just mg. Okay, great. So in this case, the friction is equal to N2. So therefore, the friction force is equal to mg over 2 square root of 3. But the friction is equal to mu mg, right? That's the standard formula for it. So plug it back in here. So that's going to be mg over 2 square root of 3 equals mu mg. And the mg cancel out. And therefore, the mu value becomes equal to 1 over 2 square root of 3. You work it out, you're going to end up with 0.29. Okay? So the minimum value, so the friction, in order for it to be, he said, what is the So what is the minimum value of mu to prevent the ladder from slipping? Well, the minimum value is that the friction, when it is less than mu mg, right? So the minimum value of the friction in this case is that when mu is equal to 0.29, okay? And then you can work it out for the friction force, whatever it is. You see what I'm saying? Okay? Okay. Okay, the next problem that I want to do is the beam problem, which is, okay, it's not an example. I believe it's a homework problem. It's kind of a cool problem, number 59. Yeah, 59. This is a typical problem that you find in mechanics, statics class, if you take in the statics class after you finish physics. I've taken that course when I was engineering major for a while, and so I'm familiar with those courses. All right, number 59. Let me look it up for you. We are in chapter 12. It's called, there it is right here, 59. Okay, good. So look at the figure here. Let me make it a little bit bigger for you. So you got this guy sitting on this beam. There is a cable, as you can see here. The cable makes 30-degree angle with the beam. Then the guy is basically the mass, right? So we're going to take into consideration the mass of the beam and the mass of the worker here. The beam length is 6 centimeters. And what is he asking? He said in the figure, an 80-kilogram construction worker sits down 2 meters from the end of a 1,450-kilogram steel beam to eat his lunch. All right, so 2 meters away, where? 2 meters, I guess, from this end right here, I think. Is it? I don't know. What is it? Oh, okay, yes, from this end. I'm looking at my diagram. Okay, so 2 meters from this end. So what is the tension on the cable? Okay. It can be a hard problem. Put it on the side like that. All right. So let me first draw the diagram for you. So here is the wall. Here is the beam right here. And then we have the cable. It's not good. I want a better cable. There we go. That's a little bit better. Okay, we have the guy. I'm just going to make him into a block like that. Okay, and this is 30 degrees. I'm going to make him theta for now. And this is 2 meters. And then we have the weight of the beam. I'm going to call it mg. Let's make it big mg. And then you have the weight of the worker, a small mg. Okay? And then, of course, we have tension in the cable, T. And I don't know the angle here, but here is a question. Oh, and then you have the full length of the beam is 6 meters. There we go. Okay? All right, you can pause the video and think about it, see how we're going to put all the forces right there. Now, initially, I could just use Newtonian physics, okay? So let's do that. That's the easy part. But before I do anything, what are there any other forces here? I mean, I put all the forces that are obvious to me: the weight of the beam, the weight of the beam, the weight of the guy, the worker, and then I have the tension. Is there something else? I mean, here, right here, you get the tension, the same thing. So that's a T here. So it just will be a redundancy. One of them is enough. What about here? Is there a force here? The answer is yes, actually, there is a force right here. And that force, I have no idea what it is. But all I know, it is some force, God knows what direction. It's going to be like that. I'm going to call it big R. And at some angle, I have no idea what it is. I'm going to call it phi. Okay, this is very important. You can't ignore that force. Obviously, there is a force there, right? It makes sense? I mean, why does it make sense? Well, imagine if you put your finger right here. Imagine you put your finger between the beam and the wall. Is it going to hurt or not? Well, there is a force there. It's pushing it. You see what I'm saying? So there is a force. And that force, it's some direction or an angle phi. Got it? Okay. So to me, I have a problem here. It's not just I need to find the tension. I need to find this R. Or do I? Do I? Well, let's see. So I'm going to be innocent about it. Okay, let's say sum of the forces in the x direction equals 0. What are they? Let's do them. So basically it's going to be minus t cosine theta, correct? Plus r cosine phi equals 0. Yes? Okay. Sum of the forces in the y direction equals 0. What are they? It's going to be t sine theta minus big mg minus small mg, right? Plus r, big R, sine phi equal 0. Okay? I mean, all right. The problem is I have too many unknowns. I have phi, yes, phi. I don't know phi. I don't know r, and I don't know t. I have too many unknowns. The rest I know, but it's just too many unknowns. Same thing with this equation. I have more than one unknown because I have one equation. I don't know phi, I don't know r, and I don't know t. So it is a problem. You see what I'm saying? So how do we solve it? Well, there we go. That's why we invented torque. And so we appeal to the torque equation. The torque equation will make the things a little bit easier. So I'm going to take the torque equals 0. Why 0? It's not spinning. The whole thing is in a static situation, correct? Okay. Now here is the question. Where are you going to put the torque? About what point? Remember what I told you in the previous problem. You put it about a point where it has vectors that you don't know anything about. What would be that point? Well, right here. Why? Because in this case, I don't need to get this darn r or phi. It will just eliminate it completely. You see the trick? So I'm going to take it about O. You understand that? That's why I'm no longer afraid of r, because I don't need to calculate it. I can just find the torque about O, and that will be eliminated. You see what I'm saying? Okay. Oops, I need to. So let's see. So in this case, the torque. So now I have, how many forces do I have? Let me change it the color. I'll use red. I hope everybody's happy with red. So here here is the distance, and here is one force. Whoops. Here's one force right here. Here's another force, and this is the torque. Of course, it's going to be sine theta, right? It's going to be this way, and that's it. And guess what? It looks like I'll be able to do it. All right, let's calculate it. So it's going to be. Let's start with the beam here, and again, it's going around like that. So that'll be clockwise negative, and this is going to be counterclockwise positive, right? So I'm going to work a little bit faster. I hope you'll know it by now. So that's just going to be -3 big mg minus, what's the mass of the guy? 80? I'm sorry, just, I mean, he has 2 here, so that makes it 4 here, right? So it's going to be 4 mg, right? And then we have plus t sine theta, correct? Times, how far is it? It's 4. Excuse me, 6. Equals 0. Done. It's really easy. I didn't even need those. You see what I'm saying? So anyway, let's continue on with it. So if you work it out, I got T equals to 15,300 Newton. Okay? Now, I'm done with the problem. That's it. Finished. We're done with the problem. And that's basically what he had. But I'm gonna go one more. I wanna go one more step for you. What if there is a part B to this problem and tells you find R and find phi? Can you do that? Would that be hard? Let me show you how to do it. So now I know T, correct? I'm going to give you a sketch of how to do it, and you work it out. Look at the first equation. We call this equation 1, and that's equation 2. Okay? Look at first equation 1. 1 becomes minus 15,300 cosine what? 30, right? Plus R cosine phi equals 0, correct? Okay, let me get that answer very quickly. So it's going to be cosine 30 is 0.866 times 1,500. So that's going to be basically, I have this equation, R cosine phi equals to 1,324. I'll make it 5. I'm approximating it. 50. There we go. I got this equation. Got it so far? Okay. Now let me do the same thing with the other one, right? I'll go up vertically. Now the second one, which is right here, I'm going to do the same thing. So that's going to be 1,500 sine 30, which is half, minus mg. So that's going to be, what is it? What is mg? 1450, and this is 80, all of that times, I'll make it plus, times g, plus r sine phi equals 0. Let me calculate that very quickly. So I have here the first one, 1,500 times 0.5. Answer, I get here to be 7,650 minus 1,450 plus 80 times 9.8. Answer 1,4994 plus r sine phi equals 0. Okay, so far? Okay. All right, so let me clean it up a little bit more. So I got 1,4994 minus 7,650. Answer. So what I have here is r sine phi equals to 7,344. I hope I did it right, but let's assume this is correct. There we go. I got those two equations now. This one and this one. You see that? Here's the trick. Let's call this equation 2 and this is equation 1. Divide 2 over 1. In other words, like that. R sine phi over R cosine phi equal to 7,344 over 1,3250. The RR cancel out. Well, sine over cosine is tan phi, right? Tan phi equal to 1,3250. Again, I'm hoping I'm doing it correctly. I got 0.554. Therefore, phi is equal to, just take a tan inverse of this thing. How do I do this with my calculator? It goes shift tan of the answer. I got 29 degrees, almost exactly 29 degrees. There we go. Isn't that cool? So after all, it's not that scary. Now I can pick one of them. Let's say I pick equation 2. So therefore, R in this case is going to be equal to 7,344 divided by sine 29. And so 7,344 divided by sine 29. Answer. So the reaction, or whatever you call that vector, there's a name to it, I forgot. 15148 Newton. There we go. Isn't that interesting? See how powerful the torque equation can be? You can actually find that. But this step is actually, this is what you'll be doing if you take a course in statics. You actually be doing those forces. Okay, great. All right, the next topic, I think I am done with the torque. I'm just going to move on to the next last topic, and that is angular momentum. It's not a tough subject, so I'll go over it very quickly. Angular. Okay. What is angular momentum? I'm sure those of you who have taken high school physics, you probably have an idea what it is, but let me explain them. For example, let me show you how the Earth moves around the sun. Okay, the Earth moves around the sun in an elliptical path. Okay, this is Kepler's. We're going to study that next chapter. Kepler's first law. In such a way that the sun is located at one of its foci. Basically, it looks something like this. Here is the elliptical path. Again, I'm exaggerating the way the elliptical path look like. But here is the ellipse, okay? And here is the sun, right here. Here is the, think of it like this is the major axis. This is the minor axis. And here is the location of the sun, right here. Okay, this is the sun. And let's say here is the Earth, okay? And here is the distance between the Earth and the sun. The Earth is going this way, okay? So it keeps going around. I'll put it in my mouse so you see the cursor. So here is the Earth right here. So it moves around like that, okay? Now, it's not moving with constant speed. As it is going about the sun, it actually increases in speed, and it reaches maximum speed right here, okay? At the point of perihelion, and then it starts slowing down until it is here minimum speed at the point of aphelion, and then it starts accelerating again. In other words, it is constantly speeding up and then slowing down, speeding up, slowing down, speeding up, slowing down, okay? It does that all the time. Now, what does that mean? Well, I'll come back to it in a second, okay? We have something called the angular momentum. Just like, momentum is mv, angular momentum, which has a symbol L, is equal to mvr. Okay? mvr. So, or I can write it because mv is p, momentum, so I can call it pr if you want. You see what I'm saying? Okay. We have something called the conservation of angular momentum. I like to write it this way, angle MTM. That's my symbol for it. The conservation of angular momentum is basically this MVR is L1 equals to L2. What that means is M V1 R1 is equal to M V2 R2. Let's apply this formula to the Earth around the sun. Okay, let's pick the Earth here. So here it has a speed v1, and this is the distance r1. You see what I'm saying? Now, what about when the Earth is here? Well, it has a distance r2 and a speed v2. Remember, we said that the speed here is actually here, v2, is faster or greater than v1. Why is that? And then, of course, here is slowest. If this is r3, and here is the speed of the Earth, v3, okay? This is slowest right here. This is fastest. And that's kind of in the middle somewhere here, okay? This is the same thing here. At any point, it's constantly changing its speed, you see what I'm saying? What's happening now, the question is, why is it fastest here and slowest here? Why is that? Well, it has to do with angular momentum. It has to do with the fact that this product, MVR, have to be the same at all time. In other words, L1 and L2 must be the same. Here, let's apply it. Look at R1 here, this is a situation 1. So here is the mass of the Earth, the velocity V1 and R1. It must be equal to the angular momentum of the Earth here, which is the mass of the Earth, same thing, and the velocity V2 R2. Well, in order for it, obviously here you have R2 is much less than R1, right? So in order for it to compensate for that loss of distance, V must increase, and that's why it goes fast. Same logic applies here. Here, R have increased a lot. See that? So in order to keep it at the same product, MVR, so that means this V must decrease because this thing have increased. Got it? That's basically what conservation of angular momentum means. Another version for the conservation of angular momentum is I omega. So angular momentum is equal to MVR. MVR is also equal to PR, and it's also equal to I omega. Remember, the torque is equal to what? I alpha, right? And the angular momentum is I omega. So the conservation of angular momentum is also equal I1 omega 1 equals I2 omega 2. I here, of course, being the moment of inertia, right? Okay, let me give you an example. I'm going to give you an example from the book. That is one that I looked at. Yeah, this one. One more thing, I just saw it before I move on. And that is, remember, okay, so we said that the force is equal to MA. And then here the torque is equal to I alpha, right? I mean, these are translational, and the comparison between them. We also know that the force is equal to dp dt. Did you know that? The p here being the momentum, so it is dmv over dt. If we assume the mass is constant, so it becomes m dv over dt, and of course dv dt is a, so it's just ma, right? You got it? Okay. So we also have the same, we have another concept here where the torque is, see here we have the derivative of the momentum, the linear momentum for the force. Here we have the derivative of the angular momentum. You see what I'm saying? And if you look at it, look at that. So this is d dt of mvr, right? And that will be equal to, take the mass out, so it becomes v, let's put it in a bracket like that. Now you have a d dt of vr. Let me put it in terms of, maybe not, it's okay. Hold on. I think I want to do it in terms of vectors. It'll probably be more obvious here. Let me write it down again. So you have tau is equal to dl as a vector dt. And we know that the angular momentum is, as a vector, is mv cross r. So let me put it in here. So that becomes d dt of mv cross r. The mass can be kicked out if we assume the mass is constant. It's not necessarily true. It can be variable, such as a rocket motion or something. But anyway, so now if I would take the derivative here, I have to use the product rule. So it becomes dv dt cross r plus v cross dr dt, correct? Okay. So what is that equal to? Any idea? Okay. Look at this. I have m, well, dr dt is v, right? So this is like v cross v. Plus here, what do I have in here? I have dv dt cross r. Is that right? This will be 0 because if you have two vectors, a vector crossed with its own is equal to 0, because if you have two vectors that are parallel, if A parallel to B, then A cross B is 0, correct? So now I have this one, M dV dt cross R. Well, that's also equivalent to the torque, and that is, remember, this is the force dV dt, right? I mean, with the M, so that would be the force, right? If I put the M here, look, so that will be dm dt cross R, and that will be the force. That's the force right here, so that will be force cross R. Got it? Okay. All right. Let me give you an example of what I'm saying here. Look at the example 1218. Oh, I can look it up. And that is example, yeah, I need to show it to you because it's kind of hard. Well, it's not very hard to draw, but anyway, section 11. This is the example, I think, isn't it? Yeah, this is the one. Okay, here's the example. What you have in here, so let's read it together. It says, look at the picture here. I'll make it smaller. Okay, it says two equal masses. It looks like a dumbbell. So you have two equal masses, this one and this one, are at the ends of a massless 50 centimeter long rod. The rod spins 2 revolutions per second. That would be the frequency, right? So this spinning around like that, as shown in the figure. About an axis midpoint right there, suddenly a compressed gas expands the rod out. So it becomes longer, okay? So somehow it becomes longer. Compressed gas expands the rod out to a length of 160, okay? What is the rotation frequency? He wants the rotation frequency. Here we started with 2 revolutions per second. And now he's asking what is the rotation frequency after the expansion, okay? Pretty simple problem. I hope it is. And what you want to do in this case is, let me draw it for you first. And here's the two dumbbells like that. There's the center. Something like that, and then you have a vertical. I'll try to make it vertical. There we go. And then you have, here is the axis. Okay, that's like omega. And then they're going in this direction like that. Okay. This is mass M, mass M. All right, so the initial length of the rod, L1, I'm going to call it, he says it's 50 centimeter. Okay, and the frequency, the initial frequency, F1 we'll call it, is 2 rev per second, which is basically 2 hertz, correct? And then later on, the lengths have increased to 160 centimeters. 1.6 meters, right? And he's asking for what is the frequency. Pretty simple problem, I hope, right? So one way to do it is to use the angle and conservation of angular momentum, L1 and L2. So that will be, I like to use the moment of inertia because it gives me that, just the nature of it. So I1 omega 1 equals I2 omega 2. Before I go any further, we know that omega is 2 pi f. Is that right? So this becomes I1 2 pi f1 equals I2 2 pi f2. The pi's cancel out, so I have an interesting relationship for angular momentum. I1 f1 equals I2 f2. Okay? The only thing left here is the fact that what is I1? Well, I1, what is I in this case? Well, I here is, he says in the problem, pay attention here. He said two equal masses are at the end of a massless rod. That means don't take the moment of inertia of the rod into consideration. Only the masses. You see what I'm saying? So what is the moment of inertia of a point mass? Is mr squared. That's it. So it is mr squared for any point mass. Okay? Had he said that there is a mass of the rod, then it would have been, well, it's 1 over 12 mr squared or something like that, right? So for our case here, it becomes mr1 squared f1 equals mr2 squared f2. Got it? Make sense? Okay. Masses cancel out. R1 is 0.5. He gives it to us, or rather we used L, I guess. I'm sorry, this is the length, the full length or the radius? Oh, it is the full length. Okay. So so in this case, let me go back here. So in this case, R1 is 0.25 meters. Is that right? Make sense? And R2 here is half of this, which is 0.8 meter. Yeah? Okay. And then we just plug it in. So it's going to be, this is not correct. So that's going to be, what is it? 0.25 squared f1, he said 2, equals, again, R2 is 0.8 right there. So that will be, oops, and that will be 0.8 squared f2. That's it. So therefore, you just solve for f2, and that should give you the answer. I'll, from the book, it should be 0.195 hertz. Okay, and there we go. Got it? Okay. I think I'm going to stop here. I think I've covered just about everything in the chapter. And however, if you have any questions, please let me know. You can post them under Ask the Professor. Like I said, this chapter, let me just go back very quickly before we finish off. Here's the course schedule. And this chapter goes for 2 weeks. And so we're going to go one more week. Don't forget that the following week on May 1st, let me do it again. Here is the calendar. I'm doing this video today on Thursday. So we still have another week. We will have the midterm, I'm sorry, 5-1. So the midterm is going to be next week. Friday is going to open up on 5-1, May 1st, and it will close on Sunday, the 3rd. Okay? Okay, that's it. Have a good week. Bye-bye.